So in this video, we'll talk about the conservation of angular momentum. Also, we'll talk about rotational energy, and then we'll go more specifically into moment of inertia, and then finish with example problem number 4. So, we'll start out with moment of inertia, with the definition, which is the quantity that determines the amount of torque needed to get to a desired angular acceleration about a rotation axis. So it's pretty much just what quantity is needed to get it spinning like at a constant acceleration. So next we'll talk about angular momentum, the conservation of angular momentum. So we can think of this as something we see. You can think about it by just thinking of the Olympics, something we see in real life. Let's just talk. Say for example, a skater. So a skater's angular momentum with radius r, and then if they bring their arms in and make it radius r/2. So, and they're spinning in circles, of course. So we can talk about angular momentum. The equation for it is angular momentum equals omega, which is angular velocity times moment of inertia. Angular velocity equals just linear velocity over radius, whereas moment of inertia equals mr squared, mass times radius squared, or the integral of radius squared dm. So now what we're gonna do is we're gonna think about the conservation of angular momentum with this figure skater. So if the angular momentum has to stay the same, so if we write this as write it where we just use r, the initial radius, it's just going to be angular momentum equals angular velocity times moment of inertia, and that's equal more specifically to v over r times mr squared. So if the skater brings in their arms to half of their initial radius, pretty much what the conservation of angular momentum says is just that they're gonna spin even faster because the moment of inertia is reduced. Because obviously mr squared, if r is cut in half, then it's going to be 1/4 of the moment of inertia is going to be 1/4 of what it was, right? So m times r over 2 squared equals mr squared over 4. So, but the angular momentum needs to stay the same, so that means that the angular velocity is going to be multiplied by 4. So pretty much when the radius gets smaller, the moment of inertia gets smaller too, which makes the angular velocity bigger. So last thing we're going to talk about is rotational energy. It's sort of like just normal kinetic energy. We can see the relationship between these equations, 1/2 mv squared, but for rotational energy, it's 1/2 moment of inertia angular velocity squared. So now we can apply these concepts to problem number 4, which is suppose that a spherical star spinning at initial angular velocity omega suddenly collapses to half its original radius without any loss of mass. Assume the star has uniform density before and after the collapse. What will the angular velocity of the star be after the collapse? What we're going to use is our formula for angular momentum. So that equals angular velocity times moment of inertia, which equals, like we were writing before, we can just simplify the moment of inertia, angular velocity times mr squared. So originally, like before the velocity was omega, so we have r just equaling r, but after we have the radius splitting in half, so we have omega. After we have omega times m r over 2 squared. So that's going to equal omega times m r squared over 4. So just like before, now we know that the angular momentum has to stay the same. So this new angular velocity 2 for after, we know that has to be 4 of the omega, 4 of the original omega, because angular momentum stays constant, and if this is r squared over 4, to get rid of the over 4, we need to multiply. The angular momentum is going to be 4 omega.